So let's say you've somehow gotten $1,000 to invest in stocks. It's the financial downturn. Of course, some people will be looking for stocks. Now you're looking at these 3 stocks. Which one are you supposed to choose? Now, obviously, we should be looking at the financials. The smart things to do. Now, let's look at the financials. What am I supposed to be looking at? What does 9 mean? Oh, you're panicking now, aren't you? You're agitated. Are you gonna walk around the room thinking about what to do? Are you gonna bounce up and down, trying to think of a solution? Or are you just gonna yell to evolve into chaos? Well, keep staring. Or we could relax. Okay, here's the actual presentation. Newcomb-Benford's law, also called Benford's law or the law of anomalous numbers. So in this table of contents, we've got the history, we have the math because it's math, and we have applications. First we're looking at history. Oh no. Simon Newcomb is the first recorded person to discover this. You can read his biography, his summary. In 1881, he noticed that in a book of logarithms, the earlier pages were dirtier than the last pages, so then he thought people were dealing more with the numbers starting at 1, then 2, then 3. So that's how logarithms work. And then there's a graph I'll show you later, how that works. He wrote a paper and wrote a formula, log n plus 1 minus log of n. However, mathematicians never really looked at his theory. Here's what he actually said. This guy is Frank Benford. While working for the GE company, he also found similar results, but then also went further and tested it on real life sets such as area of rivers, cost data, X-ray volts, newspapers, death rate, and the average of all of them came very, very close to the actual Newcomb-Benford's law. It's predominantly called Benford's law, but to give credit, I'm calling it Newcomb-Benford's law. And here's some other people using this for financial irregularities and using the law for voter fraud. Now it's the math. And if you want to skip this, so sad. Okay, fighting the math now. The graph of digits. So this is the distribution of digits, of leading digits. So 1 appears 30.1%. You can read the rest. And you can create an exponential curve. Y equals 51.478 times 0.585 to the x. And x represents the digit. That really doesn't matter. Here's the actual formula. Log 1 plus 1 already. Because logarithms are the inverses of exponentials. 0 does not apply to the first digit, obviously. Here's another way to look at it. And so from wherever P represents, you can read here, but P, this is the probability density graph, and P represents 0.301. And within those black stripes are where the leading digit will be 1. Now, why is the probability of each number not 1/9? This is a huge good question, and here is their proof. So, these are the 9 numbers, and they should have an equal probability if you were to argue that. However, if you were to double these, you would actually, 1 would become 2 or 3, and then you can see this, but then the most important thing, 5, 6, 7, 8, and 9 would double to 1. And so this has a much higher probability of happening. And then when you keep doing this so many times, this is called multiplicative fluctuations, it eventually will confirm further and further to Benford's law, because Benford's law isn't 50% 1, whatever it is. And here's the requirements. Not requirements, but it's better to better confirm with Benford's law. You need to have larger size, larger magnitude, and a smaller chi-squared result. And Newcomb-Benford's law works with larger sets of data and higher differences of magnitude. And the chi-squared test is a simple test to find the difference between expected and observed frequencies. You can also generalize beyond the first digit, and there are even ways to generalize with the first and second digit. Okay, there it is, where n represents which digit it is, and d represents the number 0 to 9. Something there, I don't remember. Explaining Newcomb-Benford's law, multiple probability distributions. There's multiple probability distributions, multiplicative fluctuations like before, scale invariance, and entropy-related explanations. Multiple probability distributions is where data sets that have uniform distribution fail Newcomb-Benford's law, but when it combined with another uniform set of another random one, it starts to reappear again. Multiplicative fluctuations, like I said, multiplying by like some within a set domain continuously will eventually lead to Newcomb-Benford's law. Additive fluctuations will not. There's scale invariance, so sets that are independent of units that data expressed in. It implies base invariance because the metric system follows a base, and then the imperial system follows another base because the metric system follows base 10, but then the imperial system is another base, and so that implies base invariance, which definitely follows Newcomb-Benford's law. And a few interesting points. You can read some of this, and it works. The most important thing, it works for all bases. And most of these things have little magnitude differences, so this is why these don't work. But these also work because of the magnitude differences. Here is the applications, because math can actually be applied to something. And you know what the biggest application is? Fraud. Combating fraud using Benford's law, or the Benford law variation I was talking about, where it analyzes both the first and second digits at the same time, or just for calculating the first and second digits individually. And you know, our friend is extremely happy at this. Faked COVID-19 case counts, Benford's law got you. But of course, it follows Benford's law. The 2009 Iranian presidential election does not as well follow Benford's law. This spike in 0, and then as well as this smoothening in the 0 in the later digits should be something like this. And that's not even the worst. It was like 7 spike. And now that 2020 presidential election, because of course, Benford's law definitely shows fraud in that. And no, it does not. When there's only small differences in magnitude, it does not show Benford's law, because this is only looking at precinct or county level data, and Trump's data just happened to follow. So this is misleading. The Enron financial crisis, if someone had actually done this before, how many billions of dollars would have been saved? No one knows. Honorable mentions, Greece's Eurozone data that they used to apply to the Eurozone was regarded as highly improbable according to Newcomb-Benford's law, and federal, state, and local courts all accept Newcomb-Benford's law as evidence, which means you could actually put in the you could actually say there was a very low chance, according to Newcomb-Benford's law, that this data would exist, and has been used to detect fraud in scientific papers. The IRS uses it. Possibly even the SEC uses it. You know what the biggest downfall is? Newcomb-Benford's law cannot prove fraud, but it may suggest fraud. And now thank you so much for going through my presentation. I know it's very boring, it's just statistics. If you have any questions, email me at my totally real contact information. And here's all the data if you ever wanted to use it. Okay, I think I keep messing up. Well, I think I know which one I'm choosing now. These two have oddly similar financial data. And okay, let's just quickly go to the SEC, because that's what everyone does these days. Complain to the SEC. Oh wow, Grammarly, I don't care about my 3 steaks. Is that it? Okay, let me click this one button. 3, 2, 1. Okay. Well, that's nice to see. 1 year later, what? Let's go visit our nice friend. Oh, he's actually bought his second monitor. Oh, YouTube notifications keep piling up. How to spend your money. Oh wow, they actually convicted them. Oh, guy's rich now. Well, maybe if you follow Benford's law, maybe you can be the next trillionaire. I don't know. Maybe make good financial data. Maybe this is just a figment of your imagination. That's it of the video, though.